with the first. Oh, thanks. Let's start with the first topic. So what parts of the radio transient phase space should we be exploring? So this is the transient phase space diagram for short duration transients. We have duration of the transient on the x-axis and luminosity on the y-axis. You can see a whole host of transients already on this diagram, but there are regions of the space that are relatively unexplored or just unexplored. So the first is the yeah, maybe Ziggy if you click the low luminosity FRBs. So this galactic magnetar SGR 1935, we've seen a whole range of luminosities from this magnetar that are yeah, all the way up to close to the FRBs and then somewhere in between the pulsars and FRBs, and then also this FRB in the globular cluster in M81 shows relatively low luminosity emission. So yeah, that's one area of the parameter space that needs to be populated. The second is extremely high luminosity FRBs, arguably the rare FRBs, really high luminosity FRBs. And then you have the ultra short duration or ultra fast transients. So most FRB surveys operate at like 100 milliseconds, 100 microseconds to milliseconds. So likely if there are transients that are nanosecond to microsecond, yeah, FRB surveys are probably not going to detect them. So we've seen that there are transients in this parameter space, like crab nanoshots, and then some timescales seen in repeating FRBs go from tens of nanoseconds to microseconds. So there is reason to find things in this parameter space. And then the last on this diagram that we identified is the ultra slow FRBs. So 100 milliseconds and above. And I think there's a discussion somewhere on Slack about what point you would stop calling it a fast radio burst. How slow does it need to be to not qualify to be a fast radio burst? So yeah, I think this is the opportunity to open the discussion on what parts of the phase space we should be exploring, why, and what kind of things we can learn about FRBs, neutron stars, by probing these areas of the parameter space. Yeah, so if anyone of the junior people up to postdoc level have any opinions or questions or comments. I guess, Ziggy, you're a postdoc, so you can also speak. You're allowed.
While people are thinking, maybe I'll just give a quick update on the poll. Currently, micro timescales, optical and X-ray, and are almost tied for the most interesting region to go into.
We have Samira in the chat. I don't know if Samira, you want to speak? I can give you that power.
Hi, can you hear me?
Yeah, hi.
Okay, hi, great, thanks. Yeah, it was just a small comment in the chat that, of course, we're instrumentation limited. I mean, optimally, we would like to explore the entire phase space of this diagram, right? But what parts of this phase space diagram can we actually explore using current instrumentation for extragalactic events? And then which part should we then focus on? I think that's more the kind of question we should be looking for, because building a new instrument would take a long time before we can actually use them. I don't know if it's included in the question, if it's also like what kind of sources should we be aiming at? Because we were lucky to detect the FRB from SGR 1935, because there's not that many radio observations towards magnetars that aren't currently in X-ray outbursts or undergoing X-ray outbursts. So yeah, I would also propose, or my idea would also be that it's good to observe and target those sources that we think might be producing FRBs to not reactive but proactive. So those would be my 2 cents.
Yeah, I definitely agree. I think in these low luminosity FRB regime, we need to target galactic objects and or really nearby FRBs that Mohit was alluding to in his talk, to try and fill in this area of the parameter space. So yeah, I guess that it maybe bleeds a little bit into the next topic of conversation about how, like, what we currently are doing to fill the parameter space. And I guess potentially Chime already have this covered, the low luminosity FRB regime. But yeah, I guess if obviously we should be thinking about what we can currently do in terms of probing these areas on the parameter space, but also if there is a valid reason to explore a parameter space for in terms of understanding the emission mechanism or neutron stars, or for whatever other reason, then if it's a good enough reason, then you're going to want to build an instrument to do so right down the line. So I think it's still valuable to have maybe more crazy ideas or wild ideas that would require a new instrument or new technology to be able to do so. Oh yeah, I see there's a lot of comments on the chat. Okay, Vivek, maybe I can allow you to speak.
Hi, thanks, Kenzie. I think what I was asking has partially been addressed with the discussion following Samara's question. So, I mean, this is not a comment or anything. Just wanted to bring the discussion to this point as well. That low luminosity burst is obviously one thing you want to explore, but they have 2 options of either going wide field of view, building more stairs, building more MWA like stuff, which are not necessarily very sensitive to deep high redshifts, but can look up bursts from M31 or Andromeda. But otherwise, we could also not spend too much and use sensitive instruments like Arecibo to target, or fast now, to target nearby galaxies and expect crab-like bursts from those galaxies to be detected. Or, what is the best way to get local less luminosity bursts?
If we're in the dream big stage of the discussion, I'd like to hear also from the audience if there's any expectations that we will find a totally different class of transient. Maybe if you go to shorter timescales or longer timescales, will this be the same as FRBs, or something completely new that we might find?
Yeah, I think that's something that Keo was saying in the chat, saying how important is that high time resolution be a blind search. rather than repeater follow-up or zooming in on something seen at low time resolution. And yeah, like Ziggy said, there could just be something new in this parameter space because we're not looking for it at all.
So I think Shrihaus yes, sent maybe you want to speak to present it, Shrihaus. Let's give him the.
I see also that Navin has raised his hand.
Yeah, thank you. So I have a question. The yellow region here corresponding to the white burst, the scarcity of any detection over there, is that because of instrumental limitations, or is that because of post-processing limitations? If it is the latter, then would it be easier to explore this parameter space to start with? Yeah, that's my question.
Yeah, I think Ziggy might have more to say on this in terms of time, but I think there's a limitation, or it's maybe, I think Ziggy's point is that it was manpower limited, and that it's possible to build something to be able to detect these longer duration FRBs, but you have to be more careful because the band moves, so you have to make sure that you're correcting for that properly in order to detect these longer duration transients. So yeah, I think it's possible with CHIME and with current instruments. It's just not being done because they don't have the capability at the moment. But yeah, I think this new detection that Daniele showed with this 3 second long FRB that has periodicity, that shows you that we should be searching for longer duration FRBs.
But there's still no conclusive evidence that the 3 second FRB is one single envelope burst, or if it's comprised of 9 individual bursts. So what I was thinking is each component being long enough. That's what I was envisioning while I was talking about exploring this yellow region.
Yeah, but if you have one, you probably have more that's like that. So more FRBs that are longer have structure and probably a period, and also highly scattered. I don't think it's just one event and that's it. And I think just based on the fact that CHIME are not sensitive to these longer duration transients, then you don't have a good handle on how rare something like that would be, because you probably are only going to see the brightest version.
Schiers, I know you've been thinking quite a bit about how to search for these long duration transients. Do you want to comment maybe on the instrumentation side of this?
Sure, yeah. So as Kenzie mentioned, and the limitation right now is that we have not thought about going too long. When we designed the CHIME pipeline, we restricted ourselves to things shorter than tens of milliseconds, and our sensitivity is quite low to longer time scales. I mean, so I don't think there is any data challenge. There is any challenge in the data processing. It's just a question of somebody sitting down and doing it. And I think it is a really important aspect to do. There is a huge phase space out there. I mean, we are thinking about FRBs coming from neutron stars, but if you go to white dwarfs, suddenly everything is 1,000 times larger, and you could have bursts. You could have all sorts of things coming out from there. So I think it is an important phase space. Perhaps to search, perhaps it might not tell us about what these FRBs are, but it will definitely allow us to discover different things.
Is there someone in the attendee list that has tried these searches before that likes to speak up and tell about their experience?
So maybe Kio wants to speak. So Kio says that long time scales are trivial computationally, but almost impossible from a systematics point of view. So maybe this is something we can discuss. Do you want to speak, Kio? I will give you the.
Hi, can you hear me?
Oh, yes, we can.
Great. Yeah, I mean, it's like, the searches, the time resolution, higher time resolution costs you quadratically in computational cost, right? So it's just really, really, really hard. And we have to think in advance before we try to do it. Yeah, I mean, I think as Triharsh is kind of trying to pull off with Chime, we can do the long time scale searches now computationally, and with data streams we have, it's just that we filter our data, we filter everything that's longer than 100 milliseconds out of our data because we just don't want to deal with all that junk, and so it's just going to be really hard to not do that. I think it's possible, but we just have to, I think it's going to be like 4 times as much work from an RFI point of view to try to deal with these longer timescales.
Would it be a good approach to then coordinate observations? Because if you have several telescopes that are not co-located, then maybe this makes this job much easier. So maybe this is something.
Using coincidences, you mean?
Yes.
Yeah. I mean, if it's RFI, if they're co-located, then then that might not help. But if they're pointing at the same part of sky, and it's far separated, maybe that's a lot easier and a lot better. I mean, just really quiet sites will help too, right? DREO is probably not the best site in the world for going after these long time scales. But this might be a FRB searches are pretty robust against RFI, but I think this is one where you want these ultra quiet sites, like the Karoo or Murchison.
So I can tell you that the experience I had from the LIGO data analysis is that once you have several observatories, you become really powerful in being able to say that something is real or not. Okay, and the RFI rates, the glitch rates that you can handle, even if you don't have like a fantastic glitch rejection, the glitch rates you can handle are huge. So this coincidence is a very strong tool. And I think if we want to go to this direction, and if indeed RFI are the limit, then maybe we can just ahead of time decide that we coordinate 2 observatories in order to search this regime.
All right. So that's
many. 2 is enough.
Right. So that's a good point. So maybe Chime outriggers should be thinking about this because assume if it's if signal to noise isn't your limiting factor, then you might make you might get a long ways with 1/8 the collecting area staring at the same place 24/7, and then of course if you're pretty convinced that that the signal you're seeing is real, you can see if it correlates, and if it does, then it's on the sky.
Yes, actually here we radio has advantage over gravitational waves, right? Because you can really check that the voltages are coherent. Good point.
Does anyone? Oh, sorry.
I wanted to ask, what about the microsecond scale fast radio burst? So I know that the computational complexity scales quadratically. Now the question is, do we have something better to do with the single dish observatories? Because it seems to me that this part of phase space can be only explored by the single dish observatories.
Well, it scales quadratically in the time resolution, but the computational cost also scales cubically in the lowest frequency search. So if you're willing to throw away bandwidth and go to higher frequencies, then you might be able to afford it.
So to be fair, I don't think once you go single dish, once you don't have like 1 million beams that you need to search, once you go single dish that you have only 12 beams, I think you can do the microsecond optimally. You don't have to throw up bandwidth. I think it's totally possible. Once upon a time, I did this computation in my paper from 2017, and I think it's totally possible. Like, it's just a matter of determination, and perhaps maybe we just need to record these dozens of beams.
Ben, you have your hand up. Do you want to speak?
Thanks. Yeah, I just wanted to, I mean, I'm sure everybody knows this, but just to remember that if you go to higher time resolution, that's many, many, many more trials and many, many more. And if you also want to go high time resolution, but then go take that same data and look for wide pulses, that's many, many more trials of different widths that you're doing. So remember how that's going to affect your search space and your search statistics.
So you're going to go from SNR 9 for discovery to SNR 10. I don't think it's going to break the, like Gaussian statistics, it's not going to break the thing. And if we are talking RFI, then I don't think the number of trials is really the issue. So Vivek wanted to say something about semi-coherent searches. Are you here with us talking?
Yeah, this is based on Jason's comment on my talk actually, that if you want to actually increase your resolution in frequency towards high DM bursts, you can actually do it, redisperse your data coherently at a given sets of DM trials, and then search incoherently around it so that you don't suffer from DM smearing that much. And that is one way of getting a higher frequency resolution without having to change your bandwidth, observing bandwidth, or your sampling rate. So this is a comment, but my question was more to what approach would be more computationally less expensive, like adding more DM trials or coherently dispersing data on the fly, or simply adding more channels or more samples.
So I think I discussed this in my paper from 2017, and basically there's so if you have some time for the burst in mind, then you can decide on the resolution of the frequencies and time, and at some point, because for every maximal DM, you would at some point need to also coherently disperse. In terms of an incoherent search, you can talk about like multi-stage search, in which you search at some time resolution, let's say, I don't know, 10 microsecond, and you can then try to pass candidates, and each one of these candidates check at half the time resolution or third of the time resolution. So this can save you some factor of 10 if that's the last thing you want. I don't know, did I answer your question?
Yeah, that is answered the question. And that seems to be more promising as well. Like, the more you think about it, it seems to be more reasonable approach.
Some time ago in the chat, Jason asked if some of the more senior members of the attendees would like to comment on exploring the parameter space. Maybe that's a good way to end this this half-hour section of the discussion. Maybe if Jim or Jocelyn, if you want to speak up.
I think Jocelyn has her hand up.
I think she can speak if she wants.
Thank you very much, Barak. It was Barak who mentioned gravitational radiation. I think we also need to keep an eye on other bits of spectrum that are developing. So astroparticle is another area where stuff may land on us that we didn't expect. And we find that there are other bits of this kind of diagram that we want to populate. So also the very high energy electromagnetic, the gamma ray, is also developing very, very fast. So it's all a bit unpredictable, to be honest. I think being ready to jump whichever way we need to jump is probably the most important. Thank you.
Yeah, that's a really good suggestion. Should really add another axis maybe to this phase space diagram. I think this was the first half hour, so I guess I'll go to the next slide to go to the next question we thought we should be discussing, unless there's any burning comments or questions regarding this.
Please do.
Barak, would you like to introduce this this question?
Okay. So what is currently being done to fill in gaps in phase space, and what challenges are we facing? So what happened to the presentation? It's something, am I the only one seeing it messed up?
No, it's okay.
Yeah,
Okay,
looks
so
fine to me, Barak.
Yeah, okay. So maybe I'm the only one. I'll just read it from another place. So do we face any algorithmic challenges to search for microsecond duration FRBs? I think I would want to hear other people about this, but I think the interferometers are currently not capable of doing this, but the single dishes can. So maybe we can talk about this a little bit, and what would be good targets to search. And another issue is, well, it's the same issue. So do we point to known repeaters, or do we want to do this blindly? What's going to be our strategy? So let's ask the crowd.
And a reminder that we'd like to hear from the junior
Yes.
attendees first.
So there's a question, are different burst morphologies a challenge? So this takes us to the last point in this presentation. So here I just included like a point. Do we want to include the burst drift into the things we search? And I think that at this point, maybe it is a good idea, because I don't know if I'm allowed to share screen. So in here, no, here. Okay. So you see this super interesting diagram. It seems to me rather like a coincidence that if you take this relation and you ask what does this relation means, it means that any like FRB that you observe travels not so much longer than its actual intrinsic duration. Okay, so if you have a wide burst, okay, then it is allowed to move only slowly. Okay, so it's so if you have a super short burst, it has to move fast in order to move at, you know, a sub-millisecond duration to traverse the band, so it has a larger drift rate. But it seems to me that this could be like a selection effect. So I don't know, maybe we want to discuss this. Maybe people from Chime want to discuss this. I'll share the presentation again. Again, quiet.
It might be a good question for if there's someone on the line who has trained a search algorithm, for example, by feeding it strange looking bursts that we've never actually detected, but it's something that's just cooked up by wild imagination. Is there someone who's tried it? How sensitive are traditional searches for out of the ordinary things, or maybe things with different 1 over nu square 1 over nu to the power something dependence?
I see Jason has raised his hand. I think you can speak.
Yeah. So it's not quite your questions. It gets a bit more related to what Barak was just asking about the burst drift. My impression, at least for the the type of sad trombone features that we've seen in FRB so far, that that it actually works quite well to just detect them at artificially too high dispersion measures, where they just kind of look more like a Gaussian peak with a high peak signal to noise. That seems to work pretty well. I don't really get the impression that we've been missing too many of those for that reason, but perhaps there's a certain level of extreme drift where it deviates so much from being able to correct it as an additional dispersion measure that we are. Maybe we're biased to the ones that just drift in a way that looks like an extra dispersion measure. So we should keep in mind that maybe there are some more extreme sad trombone things that deviate from dispersion measure plus something that kind of looks like additional dispersion measure.
What's happening? Wait. So if I understand correctly your point, you're saying if it drifts, then regular dispersion correction is gonna provide the the saving. So you're saying if I have something that drifts, then maybe there's some dispersion, this famous dispersion relation called plasma dispersion relation that would approximate it well enough that after the dispersion, it would look something like this, right? So
yeah, that's right. I mean, once if you're in the regime where the dispersive delay is kind of linear across the band and the drift is also kind of linear, then it just looks like an additional DM. But maybe we're highly biased currently in the type of drifting bursts that we found that are just in the regime that I'm describing.
So things that are really limited in subband, like if you have something that shines only 10% of the chime band, then I agree with you that it's going to be highly degenerate. Okay, but if you have something, so the chime has a relatively large fractional bandwidth. So if you have something that really drifts, like on all of the band, then I think it could be that we become very inefficient. Also, let's also remember that this drift rate, so we see very different drift rates for the super thin bursts. So if you have something very thin, okay, very thin, we allow it to drift very little, very, very little. Okay. Now imagine that you have something thin that drifts like this. Okay. Would we ever, like at this point, the degeneracy would completely break and you will become super inefficient. So maybe the orders of magnitude difference in drift rate for short bursts and long bursts, maybe that's just a selection effect. I don't know.
Yeah, well, that's basically what I'm saying, Barak. I think the ones we found so far are the cases where it's degenerate with DM, and in fact, like when the sad trombone effect was kind of first found, it was it was kind of difficult to convince ourselves that it wasn't just some extra DM type effect. It was kind of non-trivial, but there might be bursts that were really missing because of what you described there. That it's just not degenerate, and we need. I would argue that we need to get better at just searching the time frequency plane in a more agnostic way. And I'm sure there must be all kinds of interesting flare star emission, that kind of stuff in chime data, for instance, that's just being completely missed because it just looks like baseline variations or something like that.
Yeah, so if I change the music of your voice a little bit, you are super enthusiastic about
Yeah, no, I'm just tired right now. I am enthusiastic, sorry. Yay.
So there are quite a few comments on the chat about an earlier question regarding whether it's feasible for interferometers to do sort of microsecond scale searches. I think that might be worth discussing, because of course with interferometer you can either do sort of a phased array type of observation, or you just tile your field of view with beams, and there I think probably is feasible. But of course there's also the fast imaging approach, which is becoming more and more common. So maybe
I can comment a little bit.
Interferometry background can maybe comment on that a bit.
Yes, I can comment a little bit about this. So if you take like a sparse interferometer in which you create thousands of beams using hundreds of antennas, then the answer is that currently we are not up to the job. Maybe we can do it only on super limited fractional bandwidth. Maybe this is something we can do. But I think if you want to go, you want to still keep like the interferometer. If you have some structured interferometer like the VLA, there are some shortcuts you can do. And I had a project with Casey some time ago on how to not go full imaging and still have the ability to get the most of the sensitivity of the array. So basically we were trying to make imaging of these one arms, and then only as a second stage do the 2D imaging. So I think there are ways around this, and it could be worth the time to think. But there's a singular point in which if you also need to do many coherent dispersion trials, then suddenly also the correlator of the interferometer needs to work many times, because you need to not only correlate once, but correlate for each coherent trial. And because correlators are usually super designed to do exactly what they are told, then like the original purpose, then I think maybe this is going to be a barrier.
Yeah, it might also be something that Barak could look at a bit further. At the moment, they correlate the low bands below 90 megahertz, but that's a bit difficult for FRBs also with scattering, etc. But it would also be possible to do 110 to 190 megahertz part of the field of view with something like 500 antennas or half the coherent array. There, that could be interesting for a wide field of view, but they have a couple of megahertz of bandwidth only at the moment.
Yeah, I was just going to add that with LOFAR, even with the current generation correlator that we have, it's possible now to dump the international stations with 10 millisecond visibilities, and the frequency resolution is actually good enough that you don't need to worry about coherent dedispersion. And of course, if the bursts are actually, say, a millisecond instead of 10 milliseconds, you're losing some sensitivity there. I would argue you're getting some sensitivity back because you have a spatial filter then. You can isolate the source on the sky. I think that helps you win back some sensitivity again. And we have some first observations that Akshat, who's on the call, and Surya, who I think is also on the call, are working on to try and scope this out for FRBs as well. But I think we are scraping into some interesting territory with interferometers now already, and maybe Ben can talk a little bit about what Meerkat is doing as well.
Yeah, no, I can say a little bit about Meerkat, I mean, we had the ambition of doing sort of more like 76 microsecond, but then, you know, we ended up trading that for, you know, more DM space and also more beams. And so, you know, if those are the choices you have to make, is you know, what DMs are you going to look at, how many beams do you want to make, and those sorts of things. So those are the trade-offs that need to be looked at. At the moment, we're doing more like 300 microseconds in order to be able to get up to DMs of 5,000 or more. So, you know, those are the trade-offs that we all need to make. So if we think, you know, if they think it's worthwhile going in different directions in the parameter space, then, you know, then we should certainly look at that.
Maybe why are you making the trade-off? Is it because of the post-processing, like the dispersion, or is it because of the correlator? Why are the trade-offs?
Well, we have limited compute capacity, and so
yes, but what is the thing that limits the computation? What is the stage? Is it just because you don't want to do coherently the correlating of all the beams, or is it because you have so many beams and you can't just disperse all of them?
Yeah, so that we have 800 beams, and so it's about how you decide that. Yeah, so you can do up to 800 beams, and then it's about how you want to trade that off. You know, if you do 400, you could do 400 beams and go to higher time resolution if you wanted to. It's just.
I see. So it's about the beams. It's not about the correlator. So if you had to correlate, if you had to use like several coherent dispersion trials, you could do it. Is that the statement?
No, I don't think we will. I haven't crunched the numbers on doing coherent dedispersion with our current system. The beamformer is capable of producing a maximum of around 800 beams at this time resolution. But we also run into network issues as well. So,
can I just jump in and ask a question related to this? I mean, has anyone ever tried to quantify, you know, would it be better with a given interferometer to, you know, make 1,000 tied array beams and search those individually at high time resolution, or would it be just as good, if not better, to just use, say, 10 times worse time resolution, but make dedispersed images for each time step and take advantage of the, you know, the spatial localization of the source in an interferometric image? You know, like at what point is it better to just do fast imaging than beamforming?
I'm not sure I understand the difference in the spatial part of that, Jason.
Well, I think you have a more accurate spatial filter with an interferometric image than with a bunch of tied array beams.
Why?
Well, because
the baselines are the same, right?
The baselines are the same, but it depends on how you pack the beams, right? If you pack the beams Nyquist and you carefully weight them all together, but you have kind of like an eggshell pattern kind of sensitivity, don't you?
Well, yeah, that's also a choice about in terms of packing the beams. That's also, unless you have a 2D array like Chime, then, you know, that's to do with indeed what trade-offs you make between the sensitivity you're willing to sacrifice in order to get the field of view.
Yeah, well, that's part of it as well, right? Because you might not be able to cover the whole primary field of view with the tight array beams, whereas you get that with the image, right? But
that's still but an image, you don't have any less beams if you want to put them. Pixels are the same as beams in that sense, right? You're just making more pixels. There's still a lot more pixels.
Yeah, I suppose it becomes a source finding problem at that point. Yeah.
So Casey's here. I gave him permission to talk. I'm sure he's thought about this, so I don't know if he wants to comment on.
Oh, sorry, I tuned in a bit late though. So what was exactly the question?
About interferometers going to a higher time resolution.
Right. No, I think Jason and Ben's comments are pretty similar to my thoughts. I mean, yeah, it's the implementation is, of course, the effectiveness is very sensitive to the implementation, and so changes in computing are also a big part of this. So we may be surprised by say these TPUs that are coming out that could be very effective for these sorts of redundant processes.
Yeah, that came up in the last discussion session. Is there any like transformative technology that will enable this? Maybe you could speak a bit more, Casey, about why you think TPUs will maybe provide a leap.
I haven't played with them myself actually, but it's like GPUs are better, I guess, is the short summary of the way people present it. So so I think I think it has similar a similar kind of impact as what GPUs had on what we've done before.
While you're talking, Casey, there's a question for you in the chat, which is how you would do an injection analysis with a real fast-like pipeline, and if something like that is already implemented for real fast.
Let's see. Yeah. Well, generally we've done injection tests in the software level, so sort of downstream from the sort of data generation and correlator, because everything we do is post correlator, and so I think there are simple things you can ask with that kind of injection, but I think there are others who are doing better injection tests because they can do it more in a more upstream from that kind of part of the pipeline.
Thank you. There was also some discussion a while ago in chat about if we're ready for the next galactic magnetar outburst. I mean, it's clear that this galactic magnetar taught us a lot about FRBs and connecting it to magnetars, but it was also a bit of a chance detection. Like STAIR2 was purposely built for it, but CHIME only has limited sensitivity for things that are not in the main beams. Are we doing enough to catch the next burst? I mean, likely STAIR2 is still observing. I saw a paper in the archive for the plan of building Gyrex out of Caltech and putting improved STAIR2 antennas all over the world to basically map out the whole galactic plane. Is that the thing we should be focusing on, or should we do any other efforts?
I guess what you mostly want to catch for those is also the very bright bursts, to see if you can even go an order or a few orders of magnitude higher, so that you really get to the FRB energies. So then the question is if DSA would do that, or would then not even be saturated, though it's very high noise level. But that's certainly an interesting thing to start with. So.
I believe there are groups that are targeting magnetars specifically and just pointing their telescope and waiting for hours to see if it produces something like the SGR 1935 event. But maybe the problem there would be if you're pointing a really sensitive telescope, then would it saturate if it's too bright? Which, yeah, it was part of the discussion of the earlier discussion today, which some people might have attended.
So take your satellite dish instead.
Sorry, Sander?
Maybe take your satellite dish like STAIR2, and then have one at each magnetar.
Yeah.
A bit higher.
Spheres, would you maybe like to comment on how you would achieve your sub-arc-second localization with STAIR2-like coverage? I think that's feasible. I can give you permission to talk.
No, I didn't mean that Stair 2 itself can do it. I think it needs a different instrument design with sufficient sensitivity for calibration, with existing sources and so on. But I think that is what we would like to do. We would like to have, nearly 15,000 square degrees of the sky at all times, and then localize anything in there to sub-arcsecond precision.
So this is like the dream machine.
It's not. I mean, you can have sensitivities of up to 500 Jansky millisecond, right? It's and that can be reasonably done at lowish frequencies with a dipole array. So we are looking into that right now. What we would need to make such a machine.
So I was trying to compute the number of beams in my head. I think it's more than 10 to the 15. No.
No. Am I muted or unmuted? Unmuted, yeah. So you don't need to search each and every beam. You can make semi-incoherent beams. So you group antennas together and form an incoherent and form one quote-unquote station beam, and then do a coherent beam between them. So you can get sort of largish 10-degree sized beams, which you search for FRBs, and then you can dump the voltage and then do sub-arcsecond precision. So you have different stations of these antennas basically. You don't do sub-arcsecond beam for me. That would be crazy. I'm not that crazy.
Yeah, this sounds more feasible. What you just said, what you just described.
I'm glad I have your approval, Barak.
So do we want to move forward with the discussion? Casey, you can just speak.
Okay, now I can speak. Sorry, I think I was temporarily off. So I'm sorry if I missed the start of this, but I feel like the phase-space discussion kind of needs to start from a question of if what we individually are interested in, and when I think about it, I think about, are we interested in sort of the golden source, or are we interested in populations and sort of the applications? And so everyone has a different answer to that. But for example, the golden source example, SGR 1935 is a perfect example of the golden source, because someone built an instrument to find something in a new phase space, and then they found it, and now we have better models for that thing. But then there are all these sort of sort of alternate interpretations that aren't necessarily consistent with that particular model for that source, right? So maybe if we have a globular cluster host for an FRB, maybe it's hard to make it all consistent with each other. And so golden sources, the value of a golden source, and kind of changes, right? Because you can't make a self-consistent picture. Or maybe the value is that you're forced to admit that there's more than one kind of FRB. That would be important to say. So maybe the phase-space question, when I think about the phase-space question, I think of it in that way. It's like, how can we definitively address the question of the multiple origins, or potentially in a very different direction is how can you use samples or find better samples to do the applications you like to do with FRBs. But it's a bit rambling. But on the first point, maybe there's a good question on the golden source point, which is there a new source out there that would we could definitively identify as a different, is there a way to find the new golden source that would be definitively different from SGR 1935, say?
I don't know if it's a golden source, but if you find some strict periodicity, and the periodicity is, I don't know, some several milliseconds, then that's definitely not a magnetar. Right? So there could be many types of golden sources. So, I don't know, what other types of golden sources do you envision? We already have star forming inside some super weird radio source. We already had the globular cluster one.
Yeah, I think I see your point. So maybe, I think binary models are pretty distinctive from SGR 1935. So I think if there was a way to identify, very in great detail that there was a binary system at a particular configuration that produced the FRB phenomenon, that would be very distinctive from a classical, SGR.
Doesn't the 16-day period for R3 kind of separate it from SGR 1935 already?
Yeah, there's an argument there. Yeah.
Maybe this is a good bridge to jump ahead to our fourth question that we thought would be useful to discuss, and just skip over the bandwidth thing for now, because we thought it's interesting. This periodicity came a bit of a surprise, the 16-day periodicity in the first repeating FRB, and then the putative, but I think pretty clear periodicity also in FRB2021 and as Barak hinted at, detecting a strict periodicity in any of the sources would tell us a lot about the source, and also especially if you can measure period and period derivative, and you can say something about the energies. But just in meeting with the panel before the discussion today, we thought, are we doing all we can to enable these searches for both long-term periodicities and sources of the order 16 to 160 days, or maybe even longer, and also the kind of short-term periodicities like we know from pulsars. So we just have some questions we thought are important to address. So maybe people in the attendees like to comment on this or ask questions. Again, reminder, we'd like to hear from the junior members of the attendees first. It would be good to hear from those of you who have attempted to do these periodicity searches and to hear what were you missing in terms of the information that's put out by the other observatories. What is your wish list in terms of what people would publish? I read in the chat, it's barycentric arrival times, that's all.
But then it's the question of what DM you're using as well, right?
Yes.
So do you use if you're using one source, do you use the same DM, or we've seen that there's DM evolution for at least 12.11.02. Yeah, and Jason's point, at what point of the profile, so what's your time of arrival? I think you just need to be consistent, right?
No, consistency is not enough. We need to think of how exactly to do this, because we don't really know what is the right answer, right? So suppose I have these sad trombones. Maybe if the TOA is somehow married to a particular frequency, it is much easier to, I don't know, find periodicity. So just imagine that different parts of the band might have a different phase in the period. Is that is that the thing we think happening? Maybe not. I don't know.
Yeah, if you have a repeater burst with a strong sad trombone effect, it becomes very hard to say, what is the TOA? You kind of want a two-dimensional TOA.
And we want it reportable, right? Because if everybody has all the data, then sure, you can do whatever you want. But we really want to be able as a community so that, I don't know, if there's a burst from Chime, and I want to search it, then it's a slightly different situation, because I cannot decide on what is the convention myself. And maybe several different observatories. So if you look at several of the repeaters, only like the entirety of the community has enough data in order to search. So we need to think of how to report this.
Yeah, as you say, Barak, you kind of need the data itself, right? Because quite often someone's made a choice about what DM, maybe they fit for DM. For every burst individually, maybe they use a single structure maximizing DM for a data set, and all of these things affect TOAs and whatnot on a level that could potentially matter.
Navin, you have your hand raised.
Yeah, thanks. A very nice question. So I was wondering if Chime requires all its antennas for performing FRB searches, or if its antennas can be split and FRBs can be searched with different FRBs can be searched with different properties, but different antennas. For example, with different DMs or so.
Well, maybe I can answer the question. So the Chime FRB search is set to 2024 for beams that are at a fixed position on the sky and in a fixed grid. So you can't really change that grid. Although you can change the spacing between the beams if you'd like. There's also the Chime pulsar instrument that has pointed beams, so it has 10 at the same time. It uses it mostly for pulsar timing, but you can also record fold mode data and point it at the repeating source and track those sources. The issue is just that with the primary beam size, you can only track sources for up to typically 10 to 15 minutes a day, and at higher declination maybe a bit longer, but that's really your limit. Does that answer your question?
Yes, yeah. So I was wondering if this is a little bit naive and crazy. So I was wondering if simultaneously FRBs can be detected using structure maximizing DM as well as SNR maximizing DM in order to see how those DMs evolve and how many other burst properties evolve over time from a given instrument. But I don't know if that makes sense. Anyway, yeah.
Yeah, that's a good idea, and it makes sense, and I think it is being done. I mean, it's just waiting until we have long enough baselines for these sources. But I mean, for 2012 1102A and for 2018 0916B, respectively R1 and R3, we do have long timescales from different instruments, and I do think people are pretty good at publishing their best estimate of DMs, their best estimate of RMs, and those things over time, and as a function of frequency. It's just, yeah, I guess one thing we could discuss is if people think some particular source is expected to show some evolution, that we as a community devote resources to tracking this. So right now everyone is going off by their own, studying their favorite source, but and then you get sparse sampling of a few sources, but maybe we do really want to figure out if the RM of R3 is changing as a function of its periodic activity phase. And then we could say, let's all focus on this source for a while, work together to fill in that whole maybe orbital or precession phase, and fill in all those data points.
Thanks.
Yeah, so in spirit, maybe we should also discuss how do we report like non-detections. So periodicity is not only where you find detections, it's also where you are not finding detections, right? So how do we keep track of these? Because it seems to me very hard.
I mean, we do have the transient name server to report bursts, and if someone builds a database that is easy to use, would everyone be comfortable submitting all of their exposure to this database to aid these periodicity searches, or maybe do this for a small number of sources that we agree upon that are the most interesting for this?
I mean, in the most generic sense, you'd have a database of observing reports in some very specific format, and you would also have ideally full Stokes dynamic spectra for any detections in those observations, all in a single database, same format. But it's kind of yeah, Utopia, FRB Utopia would be a good name for the database.
I'm sorry, maybe I'm misinterpreting. So Jason, you're saying that it already exists?
Nope, it certainly does not exist. No. It requires quite a level of coordination to have something like that. I mean, certainly a lot of the information is in papers, but as probably anyone on the call who has ever tried to do an analysis using information from 2, 3, or 4 papers realizes there's always, you know, out of the like 10 or 20 pieces of information you need to do a self-consistent apples to apples comparison, there's always 1 or 2 pieces of information missing in each paper, not always the same type of information. Before you know, you're emailing people to say, okay, you know, what basis was the receiver, or like, are you reporting this based on the central frequency or the highest frequency? Is it the top of the channel? Is it the center of the channel? Did you use TCB or TDB? Where in the profile is this? Did you maximize structure? And, you know, it goes on and on and on. It's a total can of worms.
There's also, of course, the strong bias that we tend to publish results or detections, and we don't publish non-detections. It's also a problem.
And maybe we can get volunteers from the community to start a working group, like make a wish list. What I saw like the first order things we need. Can we build a database, and then can we ask everyone observing to submit their information to the database? Are people interested enough in periodicities to work on this and devote time?
I think you would have to make it generic enough that like any analysis that you would do based on observation reports and dynamic data, that yeah, all of that would be contained in a single database, because if it was only useful for periodicity, it would be too limited in scope, I think, to make people that enthusiastic about it. There was you know, there's this thing, the European Pulsar Timing Array, or sorry, the EPN profile database, and you know, pulsar astronomers use that all the time. It's just some simple pulse profiles of pulsars to compare to. So I think there's precedent for how valuable a resource like that would be. So I think it's worth the effort, but it's not always easy to convince people of that.
Ben, would you like to comment?
Yeah, I think it's a great idea, and I think, as Jason alluded to, you know, we tried these projects for combining data from many different telescopes, different frequencies, for studying pulsars in simultaneous observations. And even when you have all the people and all the data present, it's still a big effort to get everything properly time aligned. And so, yeah, I think if you wanted to build some sort of interface that allowed people to upload their data, it would have to have some pretty sophisticated checks and balances in place to make that useful. But, you know, it would certainly be something incredibly useful if someone found the money to fund somebody to develop it.
Yeah, I think half of the work was already done with the VO events for FRBs. There has been a lot of work done on that already, but then we also need something similar for non-detections.
I think more generally, we need one thing, which is the actual bursts, and one which is the observations, either detections or non-detections.
Yeah.
I think the bursts exists in the transient name server, but as far as I know, there's no generic observation database.
Mm-hmm.
This could, of course, be communicated over VO events as well, I suspect.
Yeah, or in other VO formats. But those usually come with data, and I'm not sure if their database version also exists.
Should we move back to question 3 now? Anything more on periodicities that should be discussed?
What do you want to discuss?
No, we skipped question 3, so I was asking if we should go back to it.
I think it's a good idea.
Okay. I'm unmuted, so I guess I will go. Yeah, so similar to we've discussed a lot about what we should do in terms of sort of timescales of exploring, that we should go to shorter and longer. So another related topic, of course, is frequency ranges. Of course, within radio, but also multi-wavelength observations to higher energies, what's most useful. Perhaps a specific question is how useful is instantaneous wide bandwidth coverage? This was done a lot for the first repeater with minimal success, in the sense that it was very rare that you would detect a burst in multiple bands simultaneously. Therefore, of course, you could argue that if you then stop doing it, you'll never find it if it happens. But it's also, as an observer, I can say a lot of work to coordinate these sorts of observations. And I think the CHIME R3 results showed that actually you can do a lot just on statistical sense, looking how the rates change and how the phase changes with the activity window, if there is one. So perhaps, yeah, through that all at once. Those are some questions we had in mind. So if there are any students who want to comment on any of these, please speak up either by raising your hand or writing something in the chat.
I mean, just looking at these two waterfall figures with the emission going all the way down to 110 megahertz, it shows that there must also be something below 110 megahertz, and the emission going all the way up to 8 gigahertz also makes me think that there must be something at higher frequencies. But then the question is maybe more for the theorists on the call, like how much does it really help us if we show that this exists? Do we put all this effort into going higher? Do we put more effort into going lower? Should we do these ultra wide receiver observations? What would be most constraining? Because it's always fun to find something new and extend the boundary, but maybe it doesn't really tell us much.
I don't see any comments from younger people. Sriharsh asked about going up to sort of hundreds of gigahertz to look for FRBs. So say this, the obvious difficulty there is, of course, you have no more dispersion measure. So I think, of course, an interferometer would probably be the better thing to use to convince yourself that it's actually some sort of compact radio burst from some galaxy somewhere. But I'm sure you guys do have any suggestions on how to do this with something like a CMB telescope without DM. I guess you could look at polarization. Oh, I have to make him on. Okay.
Yeah, I mean, I don't know what the RFI situation is like at hundreds of gigahertz, and so when SPT and others observe, I don't know what their RFI situation is. What I do know is they read out the detectors very fast, and the strongest source of these transients is sort of cosmic rays, which mimic very short bursts of energy, and that can cause challenges. So I think the challenge is to identify a bunch of photons coming together versus a cosmic ray hitting your detector and dumping energy. But you're right. I mean, if there is RFI or something, it's going to be really hard to identify, an FRB from something else. Ideally, what you would like is to have two similar two micro CMB telescopes pointed at the same direction in the sky, but that's usually unlikely.
I see Ben has his hand up. Was that remaining, or do you have something new to add? No. No worries. Yeah, so I certainly think pushing it to higher frequencies would be interesting, but obviously you quickly run into technical, many challenges, small beams, very little dispersion. If we use our instincts from pulsar land, then they get harder and harder to detect the higher frequency you go, generally speaking.
Because you suspect they become weaker and weaker? But
Yeah, most pulsar-like emission has a very flat, very steep spectrum, so they get weaker at higher frequencies. Notably, magnetars are an exception, but
I remember this magnetar near the center of the galaxy that for some obscure reason like had a super unusual fluence at very high frequency, right?
Yeah, like I said, one exception to the statement is magnetars. They tend to be flatter and can be detected at higher frequencies.
Yes, so maybe that's actually a good argument why we do want to search them, because we've already seen at least one magnetar do this. So if magnetars are indeed responsible for some family of the FRB population, then maybe this could be actually something characteristic. I don't know.
Zander, you have a comment?
Yeah, so I do think wide bands or instantaneous wide bandwidth coverage is interesting. So we have the result in Pastor Marizuela and Pleunis from R3 that emits at different frequencies. And the question is this true for all or for many of the repeater FRBs, or is it just this one that is in a very special environment? Is it linked to the emission mechanism or just the environment of this particular source? So it would be interesting to do more of those. And also, is it like, do we only see one patch for these bandwidth limited pulses, or is it multiple patches over a wider frequency range? That I think would be interesting for theory to be able to need to answer that question, but then they first need to know which one it is. So there should at least be some more wideband observations to be planned.
Yeah, but there's a paper by Majid et al. Where they show for 121102 that simultaneous SX observations is detected in S and not in X. Oh, and then yeah, Aaron's commenting on the wideband K-band system on the DSN. So yeah, it's also been shown for 121102, which probably has a completely different environment from R3 based on the RM, persistent radio source, etc. So yeah, maybe this is not related to the environment and more on the emission mechanism. But I agree with the wideband observations being useful if you can see multiple of these clumps in the same band. That would be very interesting.
So Aaron, do you want to describe the search you've done in K-band?
Sure. Yeah, so the DSN has this wideband K-band system. It's the dish in Australia. So we can tune from 17 to 27 gigahertz, but we have 8 gigahertz of bandwidth dual pole. We've been using it to do FRB searches, but sort of limited in scope in the sense that it takes a long time to process. So we've mostly just been doing repeaters. But we're doing sub-banded searches and so forth. The analysis is still ongoing. I have one sort of thought, and this is more a question for the community. We've done high frequency searches of repeaters at least, and R3, to my knowledge, there hasn't been a detection above 2 gigahertz. The Gajar detection is at 8 gigahertz, but we've observed at high frequencies quite often. I'm wondering if this is just characteristic of repeaters not having necessarily frequent emission at high frequencies, or if people are thinking about going to high frequencies to do all sky searches with possibly a higher field of view. It's not clear to me. Maybe the emission at high frequencies is different for apparently non-repeating FRBs. I don't know. What do others think about this?
Just a quick note, there is a 6 gigahertz detection of R3.
It took a lot of observing time to get though, probably, right, Laura?
Actually, once we predicted where we thought the window should be, we detected on the first try. So, order of tens of hours in total. But like I said, once you do the bias search, it happened pretty quickly, actually. Yeah, and sorry, there's a lightning talk. So go check out a lightning talk. Surya Vithapudi's lightning talk shows it.
So that was predicted.
Well, actually interesting dual band R3 GMRT detection. So in two of the GMRT bands simultaneously.
Was that before the aperitif detection window or the start of that?
It precedes the aperitif window, yeah. So
the earlier might have been in the chime window, which would have been later. If you would target that, then you would be unlucky. That's not good.
In terms of Aaron's point about searching for transients in the higher frequencies, I definitely agree, because I think it's clear we don't understand the spectral behavior of FRBs with like 121102 having only been seen once by chime. And we're doing a lot of follow-up of chime repeaters at higher frequencies, but maybe these are just a specific class of sources or classes of sources where there are other sources out there that are highly active at higher frequencies that, yeah, again, we're not searching for. We're searching in like the 600 megahertz and then an L band as well. But then this relates back to the problem before of being able to detect bursts if they don't have much dispersion sweep at higher frequencies. So then you have to have more than one dish on source at a given time. Yeah, I believe that's potentially a problem with the K-band data, Aaron. I don't know if you have thoughts on this, or if, yeah, the RFI is just, there's nothing there that any detection is a detection. I'm not sure.
Yeah, the RFI environment is super clean.
I think it would be really worthwhile to do a blind search at high frequencies, because we often say these things about, oh, FRBs, they span this bandwidth from 110 megahertz to 8 gigahertz, but it's really only 2 repeating sources that span this bandwidth, and for the rest, we don't really know. So I was also thinking, and I'd like to hear other people's thoughts on this, is we could try to set up these instantaneous very wide bandwidth coverage of a blind search and like point a higher frequency telescope at some part of the chime's field of view. And then if we detect any one of FRBs with chime, you can see if there's any emission also at a higher frequency or at lower frequencies. And then we can, for the first time, say something about their instantaneous wide bandwidth of one of FRBs, because it seems clear that there's at least some separation between the two populations. So I don't think it really works anymore to say something that an repeating FRB does is something characteristic of FRBs. Are there any thoughts on how to best set this up? Or are there other telescope combinations that would be ideally suited for this, the blind search with very wide coverage? Yeah, I read in the chat, so Surya, you say if you want to do a blind search, you can't beat chime field of view. I don't think that's the point. I mean, if for just one FRB you detect, you can say something about the instantaneous wide bandwidth. You've learned something. You don't have to do it for all of the FRBs are built like a higher frequency instrument that has the same field of view. It's more thinking in terms of how did Casey call it before, golden sources. If you just one where you learn something new, and then try to extrapolate to the whole population.
Yeah, well, if you have one, I guess you could point a smallish single dish at some of the beams in chime, and occasionally at some point you'd have one in the right spot, and you could do a simultaneous multi-band. I mean, I'm suggesting chime specific because then at least you have it at the lower band, you have some reasonable rate of detection, and then whether you see something in the higher band, you don't have to wait until something pops in with a smaller beam.
Yeah, and from the first catalog, we know the rate, so we can tell how long you have to wait until you find something.
There's of course, people who have started or who are familiar with doing searches with single dish telescopes know that you have to wait a very long time for you detect something. If you're trying to do it at higher frequencies with even smaller beams, you have to wait even longer. So that's the.
If there's no more comments on this topic, it would be interesting maybe to hear about those of you who answered other in the poll of what range of phase space to explore next. So I see that Sergey and Vivek and Rui and Ron, you all voted other. Do you maybe want to comment on why or what you think we should be exploring? As we speak, we get another vote for other. Zorwar, do you want to comment? If you're online.
Or does anyone have any other suggestions for sort of areas of phase space that we haven't already covered? Sergey suggests looking for more distant sources, and he means not just looking for higher DM sources. So I can try to.
I could is anyone interested in oh sorry, maybe Sergey should go first.
No, I just have a question, because Clancy in his talk demonstrated that maybe sources with large dispersion measure are not actually that far away. And if we're looking for faraway sources, then cosmological effect due to redshifts become important. And I just wonder, are there any new ideas how to look for faraway sources which might be shifted to lower frequency, widen maybe a little bit because of the redshift, and probably have not so low dispersion measure, of course, but not just following the famous relation?
Jason, do you want to comment on this?
I had something else that I wanted to inject. It's a little bit related. I mean, I was wondering if anyone is interested in searching the ultra low DM space, like looking for not so extreme coherent emission from magnetized stars, white dwarfs, and whatnot on millisecond, second, sub-millisecond timescales. It's kind of challenging because of RFI. I think you can maybe get around that with the distributed interferometer. I mean, we're really focused, of course, on like extreme astrophysics, so it always has to be further away and more energetic or more this, more that. But I think there's scientific arguments to be made for studying magnetic activity or magnetospheric activity from more normal type stars and from white dwarfs as well. And certainly like a lot of the work that like Joe Callingham and Harish Van Dantum have been doing with LOFAR really shows that there's a lot of phase space to open up there for yeah, magnetospheric activity from more normalish stars than what we're talking about here. There might even be like a broader astrophysical community interested in that, or well, you would reach a different astrophysics community by doing those types of searches. And of course, one of the holy grails is finding that type of emission from a planet, an exoplanet star interaction, kind of like an amped up version of the Io Jupiter interaction. That's one of the holy grails as well. So yeah, I wouldn't be too myopically focused on trying to find things outside our galaxy.
Ben, you have a comment?
Yeah, I was just going to follow up on what Jason said. I mean, it was one of the goals that we had for the MeerTrack project was to try, we were sort of, the proposal was written long enough ago that FRBs weren't actually at all very common. And so the aim was indeed to do what you said, was to try and be agnostic about what we were calling a fast radio transient as a sort of fast radio burst, and try and search for those things in the galaxy as well. But as you alluded to, the DM and broadband RFI are a real issue. Even with a bandwidth of 856 megahertz at L band, like Meerkat has, that is still problematic for things that many of the things that we might expect to detect from stars and things like that are going to be relatively broad by comparison. And so they tend to be cleaned out very nicely by your 0DM filtering, for example. So yeah, it's certainly something worth trying. I mean, the other thing is, and I think this comes back a little bit to the FRBs with more complicated profiles question, is that, many of these sources are not going to have, if it's like a, what are they called on the sun? The S bursts and things like that on the sun. They have much more complicated structures, even if you do de-disperse them, than a simple Gaussian match filter might optimally extract. So there are a bunch of challenges, but we are. I think, and I'm not sure about Chime's DM cutoff, but I guess it's not that low. But we actually do have a DM cutoff at 20 at the moment, just because otherwise we get flooded with stuff. But we are still finding things in the galaxy.
So Ben, do you think it would be possible to make some filter? So Meerkat is an interferometer, right? So
yes. Yep.
Just based on the fact that you have several antennas, you can decide if something makes sense to be in the far field or is it not? So maybe it's possible to reduce the dependency on DM?
Yeah, it depends how you're doing your detections, I think, and where you've placed your beams, right? So it's going to be the best way to do that is going to be your spatial extent, right, of the as you see it. So so I think you'd need to place your beams close together to do that, and we don't presently do that. So I haven't calculated the numbers to work out where our Fresnel limit is, but
I think it's quite far.
yeah, well, we're predominantly only using the inner kilometer, so that also. But,
Just a quick note that like at low far frequencies, as Ben well knows, finding a pulsar at a DM of 1 or 2 or 3 is pretty easy. You can see the DM sweep pretty easily. So I think finding millisecond transients with DMs of a few or even less, if they're there. I think there's enough dispersion to make it happen at those frequencies at least. One of the things that might be really interesting actually is I think the radio sky is still really poorly explored at tens of megahertz at sufficient sensitivity, time resolution, angular resolution. And as I guess probably a lot of people know, there are radio emission mechanisms other than what we've been discussing, even though we don't really know what it is exactly, and other than synchrotron as well. I mean, there are emission mechanisms that cut off at a few tens of megahertz or so, and there could be some exceptionally bright transients out there at 20, 30 megahertz that only last for milliseconds that we've just completely not seen so far, even though they would be obvious in such searches.
I'll quickly add in here, based on what Ben was saying, that at most also we do see a lot of low DM signal due to RFI, which seeps into our fan beams or tight beams in which we search for FRBs, and it becomes a problem. And so the solution that we have actually also thought of is similar to what Ben was suggesting, to use the spatial information of how far that signal is spread in beams. And there's a poster by Ayushi, which is on display right now, which talks about developing a machine learning algorithm which uses that information. So not just learning how an FRB looks in a given beam, but also learning how an FRB looks in beam surrounding the main beam. And that kind of is helping to rule out low DM RFI. Like we can probably now go down to lower DM candidates without worrying about local RFI seeping in there. So this may be, we are still testing it out. It's in development, but maybe a successful project. And other thing that I just remembered was why I voted the other in the survey is it's probably has been discussed is we should probably also think about going towards lower frequencies in FRB searches. We have seen repeat FRBs from known repeaters at hundreds of megahertz, but we haven't found many new FRBs at those frequencies. And obviously they are good for finding higher DM FRB, higher redshift FRBs, because they would be redshifted to lower frequencies. And also, as Jason was just saying, there might be exotic kind of bursts in those frequencies that we haven't been looking at. So that part of parameter space maybe needs more exploration.
Has anyone tried searching for fast transients just using like DM searches with Stokes V, or DM searches searching over RM space simultaneously to try and beat down R5 false positives at low DMs and whatnot, really assuming that the source is 100% circularly polarized or 100% linearly polarized, and using those dimensions as well to pick out the signal from all the other garbage. I mean, that's been done in some imaging surveys, right? Particularly to look for like flare stars or exoplanets and whatnot. You can use polarization to your advantage. I'm not sure I've really seen that used for fast transient searches before.
I was just going to say, Jason, I mean, I think it's a very interesting idea. The problem, again, for interferometers at least, is that it means you need to make 4 times as many beams. Or you decide you throw away your Stokes I beam and only make a Stokes V beam, say. So again, it's an issue of what do you do, your data rates and your processing capability and where you focus it.
Yeah, so just going back to the poll, it seems like there's a general consensus that going to narrower time scales is valuable. And of course, similarly, going to optical X-ray and gamma ray is valuable. Followed by periodicities, and then polarization. As we just touched on that a bit, we haven't had much discussion on the polarization range of phase space. I guess perhaps the key there is just to have a larger sample. We don't have a really huge sample of polarization properties compared to the shocking size of the full population these days. Anyone have any comments on what more polarization information or more polarization properties might eventually tell us, how we might do things differently in order to do it better or faster or whatnot? Xander, do you have a comment?
Yeah, one thing I found interesting this week was about the alternative for R1 that might be in a very high magnetized environment, but we could not measure that. So it's either really unpolarized or the RM was above 10 to the power 6. It would be good to be able to measure also those high RMs somehow.
I don't know if this was attempted for this paper, but it is possible to do coherent de-rotation. It's something that is described in Ryan McKimpton's paper on the polarization pipeline for chime data.
So into what RM can chime measure?
So if you do coherent de-rotation, like coherent de-dispersion, there's no limits, basically.
But again, maybe something only single dish telescopes may consider, right? Because you do need access to voltages.
Oh no, but so with chime, for example, and many telescopes are able to do this now. Is upon detection, save the complex voltages of the full interferometer, then repoint those, and you have all the information, high time resolution, and polarization.
So you mean not as a blind search, but as a
No, in the blind search. So in the blind search, we search incoherently, but upon detection, there's a buffer of data from all the antennas, and you just save the buffer to disk. Yeah, and I mean, I believe almost all telescopes are currently able to do something like this. So I think I agree with Laura there that it's certainly super interesting to learn more about polarization, but we don't really seem limited at this point, except for getting the data and analyzing the data, unless I miss something.
I think that's true, and I think polarization could help to create populations or understanding of populations in even the current FRB sample, like from chime, for example, because we are seeing that repeaters have, in most cases, kind of a distinct polarization signature. And yeah, there's the one repeater from the Luo et al. Paper with PA swings and lower linear fraction, but I think it's possible that repeaters have this characteristic description and non-repeaters don't necessarily follow that, which would be interesting to understand why. But yeah, I think we can do that already. It's just manpower.
Yeah, so we're nearing the end of the 2 hours. Does anyone have any final thoughts on the radio transient phase space they'd like to comment on, or give any predictions or suggestions before we end? Okay. I'm guessing those of us are, well, many of us are hitting the Friday afternoon or late, whatever, third day of conference energy slump, perhaps.
Okay, if it's the end of the activity window, I will.
We might be reaching the end of the activity window.
Okay. Let me stop the
It
recording.
depends on people's frequency as to whether they've reached the end.
Yeah. There's some very high energy people on the call, but maybe they're, yeah. Okay, no more jokes. I'm going to stop the recording.